Hello everyone. Today's video lecture will focus on nucleophilic substitution reactions of alkyl halides. In the previous lectures, we have discussed the elimination reactions of alkyl halides. Now, along with this elimination reaction, alkyl halides also give substitution reaction commonly known as nucleophilic substitution reactions. Now, so the heading for today's discussion will be nucleophilic substitution reaction. Nucleophilic substitution, written as SN, substitution nucleophilic. So, these alkyl halides are the most controversial compound of all the organic compounds. Now, these alkyl halides under a given set of condition always occurs parallel reactions. Substitution as well as elimination reactions goes parallel. The only thing is, under a given set of condition, the quantity of substitution may increase and the quantity of elimination may be suppressed. If with the same reactant, same reagent, if the reaction conditions are changed, then the quantity of elimination may increase and the quantity of substitution may decrease. So otherwise, these alkyl halides always give you substitution as well as elimination. Both are occurring simultaneously. That is what we call as parallel reaction. So we have discussed in detail about the elimination reactions in different pathways. Now we are going to focus on substitution reaction. So in this, look at this. We have an electron alkyl halide. This is alkyl halide. These alkyl group may be primary, may be secondary, or may be a tertiary alkyl halide. Now these alkyl halide, look at this. Halogen is more electronegative than carbon. So when we say halogen is more electronegative than carbon, this shared pair of electron is shifted more towards halogen. So halogen equals partial negative, carbon equals partial positive. Because of this polarization of Rx bond, carbon to which halogen is directly bonded is acquiring partial positive, means electron density is decreased. So as the carbon electron density is decreased, this carbon, this is electrophilic in nature, electron deficient. So we have an electrophilic carbon. So this electrophilic carbon can easily be approached by a nucleophile. So we have a nucleophile. Let this be Nu. So this nucleophile will replace this X minus. So in this reaction, this is the electrophilic side. This electrophilic side will be attacked by nucleophile, and this X minus, which is known as the leaving group, leaves the system with its electron pair. So such that this nucleophile replace this X minus. So that means when we compare the nucleophilic character of Nu minus, the incipient nucleophile, and the leaving group X minus, this Nu minus must be a stronger nucleophile. That means a stronger group replaces a weaker group. So the stronger nucleophile Nu minus replace a weaker nucleophile, and this is what we call as substituted product. Now this nucleophilic substitution SN mainly occurs by two different pathways. Similar to elimination reaction, Elimination reaction of alkyl halide occurs via three different pathways. Similarly, this substitution reaction of alkyl halide mainly occurs through two different pathways. There are a number of pathways, but we are mainly focusing on two different pathways, which is the most common mode of substitution. So this SN, substitution nucleophilic, is of two types, means based on the pathways or the mechanism, this is of two types. First one is SN2, the second one is SN1. So we have SN2 and SN1 pathway. So now we are going to focus in detail about this SN2 and SN pathways for this nucleophilic substitution reaction. This is types of nucleophilic substitution reaction. So coming to the most common, this is the most common mode of substitution. SN1 is less common compared to that of SN2. So starting with this SN2, we are starting with SN2 mode of substitution or SN2 pathway. First of all, let's see what is SN2. S for substitution, N for nucleophilic, 2 for bimolecular. So this is substitution nucleophilic bimolecular. So as the term represents bimolecular, molecularity of this substitution reaction is 2. So these 2 stands for molecularity. So the molecularity of the reaction is 2, meaning thereby in the rate determining step of this reaction, 2 molecules are involved. This is the meaning of molecularity being 2. This SN2 reaction is a single step reaction. So reaction occurs in a concerted step, that is single step reaction. A reaction occurs in single step. This SN2, which occurs in single step, proceeds via formation of a transition state. Proceeds via formation of a transition state. So whenever we have SN2 reaction, always reaction process by formation of transition state. So transition state means which is assumed to occur in this particular state, but these cannot be isolated from the reaction mixer and their properties can be studied. So this is the meaning of transition state. Now this SN2 reaction, the kinetics of the reaction. Kinetics of the reaction says the rate of reaction is equals to some constant K, that is the rate constant, concentration of alkyl halide, so I am using this Rx as alkyl halide, and the concentration of nucleophile. So the reaction is first order with respect to alkyl halide, first order with respect to nucleophile. So therefore the order of reaction is 2, first order alkyl halide, first order nucleophile. So if you look at this kinetics, the rate of SN2 reaction is directly proportional to the concentration of nucleophile. Means for this SN2 reaction we require a strong and a concentrated nucleophile. strong and a concentrated nucleophile. So nucleophile must be strong and concentrated. So if the strength of nucleophile is decreased, the rate of reaction is found to decrease. So all successful SN2 reaction must be carried out by use of a strong and a concentrated nucleophile. Now coming to this next part. Now we have this SN2 reaction. Nucleophile will replace this X minus. Now this attack of nucleophile always takes place from the rear side of the leaving group. This is the leaving group which is leaving the system, and this nucleophile has to approach exactly at a distance of 180 degree, that is from the rear side. If this is the leaving group, then attacking nucleophile should be from the rear side, that is back side attack or rear side attack by the nucleophile. So nucleophile always attacks from the rear side, that is at a distance of 180 degree from the leaving group. So frontal side attack is never observed in case of SN2. Why this is not observed, we'll discuss later on while discussing the mechanism of the reaction. Now for this reaction, now look at this. Since nucleophile always attacks from the rear side, that is at a distance of 180 degree from the leaving group, if the starting compound is a chiral compound, that means if the starting compound is the carbon having 4 different groups, then we say that is a chiral carbon. So if the starting alkyl halide is a chiral compound, then the final product formed will have its configuration totally inverted. That means if the configuration of starting alkyl halide is S configuration, then the product will be R configuration. If the starting alkyl halide is having R configuration, then the product will be S configuration. So that is 100% inversion of the configuration if the starting alkyl halide is chiral. This 100% inversion is what we call as Walden inversion. %% inversion of product if the starting alkyl halide, if the starting alkyl halide is a chiral, that means if the starting compound is having S configuration, this is reactant, this is product, and this is reaction values of a strong nucleophile. So the starting reactant is having S configuration, product will have R configuration. So 100% inversion of configuration. If the starting compound is having R configuration, the product will have S configuration. So this 100% inversion of configuration is observed in SN2 reaction if the starting alkyl halide is chiral. This 100% inversion of configuration is known as Walden inversion. So Walden inversion is nothing but inversion in the configuration of the reactant and the product after the course of reaction. That is Walden inversion. So for every SN2 reaction, if the starting alkyl and chiral end, to 100% inversion of configuration will be observed. If the starting alkyl line is not chiral or achiral, so there is no question of 100% inversion product that is being formed. Now we have alkyl halides. These alkyl halides may be of different types, maybe have a primary, secondary or tertiary, and this may be alkyl fluoride, chloride, bromide, iodide. So we have to find the reactivity order of different alkyl halides. The reactivity order of Rx. Look at this. If alkyl group is same and different halogens are present, then Rf is the least reactive, followed by Cl followed by Rbr and Ri. Alkyl iodides are the most reactive for this SN2. Why this is so? Because look at this. As the size of halogens increases, bond length increases. As the bond length increases, bond strength decreases. As the bond strength decreases, tendency for breaking of Rx bond increases from fluorine to iodine. So, if the breaking tendency of Rx bond increases, then there is increase in the rate of a reaction. Now, if the alkyl group is different, halogen is same, then the tertiary alkyl halide is the least reactive, followed by secondary, and the primary alkyl halide is the most reactive, and methyl halide. So that means as the branching of the carbon to which halogen is attached increases, or as the steric crowding increases, the reactivity of alkyl halide towards SN2 reaction decreases. So the most reactive alkyl halide for SN2 reaction is methyl halide is the most reactive, or we say primary halide is the most reactive, and tertiary is the least reactive. So this is the reactivity order. Now these SN2 reaction, normally look at this, we need to have a solvent for this reaction. The solvent used for this reaction is normally a polar aprotic or weakly polar solvent. Solvent is either polar aprotic or weakly polar solvent. So either we can use a non-polar solvent. If non-polar solvent is not available, then we can use polar aprotic solvent, or we can use a weakly polar aprotic solvent. If the polarity of the solvent is increased, then the rate of SN2 reaction will decrease. So solvent plays a very important role in SN2 reaction, that is substitution reaction. So these are some of the general features of this SN2 reaction. Now we will explain this SN2 reaction by taking its mechanism. So let's go for the mechanism of SN2 reaction. Mechanism of SN2 reaction. We have alkyl halide. Look at this. This carbon is attached to 4 different groups. So we are using a carbon which is attached to 4 different groups. This is the leaving group halogen. So we have R1, R2, R3. These R1, R2, R3 may be hydrogen, may be alkyl group. If this is alkyl group, this may be primary, secondary or tertiary. Okay? So I'm just specifying, not specifying whether this is alkyl group or hydrogen. These may be hydrogen or may be alkyl group. If alkyl group, may be same or may be different. Now this is to be reacted with a nucleophile. So when this nucleophile attacks, so these nucleophile, as I told you, there is always a rear side attack by the nucleophile in which a transition state is formed before formation of the product. So these nucleophile, look at this. This is a nucleophile. So these nucleophile is attacking this electrophilic carbon because of this electron withdrawal by halogen. So when this nucleophile approaches this electrophilic carbon, these X minus leaves the system with the electron pair, and in this process a transition state is formed in which, now look at this, we have this carbon, so this is R1, R2, R3, and both the groups that is X, this is NU. Now during the course of reaction, the negative charge is transferring from nucleophile to X. So this is delta minus and this is also delta minus. So this is what we call as transition state. Now finally this transition state is converted into the product. So we have this nucleophile. So this is R1, R2, R3. So if you look at this, the starting reactant and the final product, there is something like inversion, tetrahedral inversion. That means when we take this umbrella, inverted umbrella. So this is what we call as tetrahedral inversion. So this is the reason why we observe an inverted product during this SN2 reaction. Now let's go to the features of the important features that we have discussed in SN2. Now look at this. Before this, the starting carbon, this carbon is having sp3 hybridization. So this carbon is sp3 and this is tetrahedral. Final product, this carbon is again sp3 and tetrahedral. The only thing is these two have configuration inverted. Inversion of configuration. So the configuration of reactant and the product is inverted. Now if you look at this, in the transition state, the carbon atom is bonded to 5 groups. 1, 2, 3, 4, 5. So now the question is, can carbon have valency 5? So the answer is obviously no, because carbon cannot expand its valency beyond 4, because carbon does not have vacant d orbital. So the valency of carbon cannot be 5. Cannot be 5. Yes. If the valency of carbon cannot be 5, then what is the nature of this carbon in the transition state in which this is attached to 5 different groups? Surprise. Now look at this, we have this answer. Now in this transition state, this carbon, first this carbon is sp2. So when the carbon is sp2, this is always planar, so we have a planar. So during the course of reaction, a tetrahedral carbon is converted into planar form, this sp3 to sp2, and then finally this sp2 is converted into sp3, then is from planar to again tetrahedral. Now look at this, why this is sp2? Look at this carefully. Now this nucleophile is approaching this electrophilic site. As this nucleophile brings along this electron pair, bonding tendency occurs. As the bonding between nucleophile and carbon occurs, this carbon halogen bond starts to break. So there is simultaneous bond formation and bond breaking takes place. So during the course of reaction, look at this carbon is freeing up. Look at this, as this bond breaks, carbon gets one vacant p orbital. Now this nucleophile attacks the lobe of p orbital and this moving away from carbon. So because of this, these two groups, distance between these two groups, this must be 180-degree distance. So I'll explain why this is 180-degree distance. So first of all, look at this. This carbon is sp2. The nucleophile and the leaving group both are attached to the two lobes of the same p orbital. Carbon halogen bond breaks, a p orbital is developed. So this p orbital has got two lobes. So this is the developing p orbital. Nucleophile attacks this lobe and halogen left this from lobe. So both these halogen and nucleophile is attached to the two lobes of the same p orbital. So these lobes must be at a distance of 180 degree. So this is, and these groups R1, R2 and R3 is perpendicular to this, the plane of this nucleophile or X minus. So these three groups R1, R2 and R3 is forming like a spokes of a wheel, and this nucleophile X, this is acting as an axle. So we have this sp2. Now look at this. We had discussed earlier the reactivity order of X alkyl halide. The alkyl halide was the most reactive. The reason is here because in transition state there is a breaking of CX bond. So breaking of CX bond is a requirement for this SN2 reaction. Now as the C and X bond strength decreases, breaking tendency will be more. So the weakest CX bond is Ci bond. So in the transition state, Ci bond being the weakest bond or the longest bond, breaking tendency will be more. As a result, alkyl halide is the most reactive. Now take the first part. If we have same alkyl halide, alkyl groups are different, then the primary order methyl was the least most reactive and tertiary was the least reactive. Now look at this. These transition state, carbon is attached to 5 different groups. 5 different groups. Now as the carbon is attached to 5 different groups, we say this is sterically hindered carbon. As this is sterically hindered means if the size of R1, R2, R3 is bulky, if you have 3 bulky groups, that means if this carbon is surrounded by 3 bulky groups, means then the space required for this nucleophile to approach carbon will be less. As nucleophile cannot approach the carbon due to the steric crowding, formation of transition state will not take place. If the formation of transition state does not take place, then there is no formation of product. For this product formation, nucleophile must approach electrophilic carbons. For this, there must be space around this carbon so that nucleophile can easily approach. So if the size of R1, R2, R3 is small, then nucleophile will have a much larger space to approach this electrophilic carbon. So this is the reason sterically hindered system, nucleophilic attack space will not be available, rate of reaction will be slow. So if R1, R2, R3 happens to be hydrogen, being the smallest in size, this nucleophile can easily approach electrophilic carbon, resulting in the formation of transition state to the final product. If the size of R1, if hydrogen is replaced by alkyl groups, so the size of alkyl group being greater than the size of hydrogen, so the space for nucleophilic attack will be less. As a result, the rate of SN2 reaction decreases. That means steric factor, any factor which increases the steric hindrance decreases the rate of SN2 reaction. This is why tertiary was the least reactive, primary was the most. Now, as I told you earlier, this reaction is single step. This is a single step in which transition state is assumed to form. Now, during the course of reaction, look at these two molecules are involved, that is alkyl halide and nucleophile. So, since two species are involved, the molecularity of the reaction is 2. Now, this reaction requires formation of transition state in which simultaneous bond breaking and bond breaking takes place. So, this requires nucleophile. So, the rate of SN2 reaction is proportional to the strength or the concentration of nucleophile. So, nucleophile must be strong and the concentrated for this reaction to take place. Now, next part of the reaction says, this located is transition state. This transition state located, there is a charge separation. So we have a nucleophile which is negatively polarized, X minus which is negatively polarized. If we use a polar protic solvent, this nucleophile will be stabilized by proton, because the same species having a negative charge can act as a nucleophile or can act as a base. So we have this Na minus. If the solution contains or the solvent contains polar protic solvent, then proton will react with this nucleophile. So this nucleophile will be stabilized. As the nucleophile is stabilized, the reaction cannot take place. So for this, the requirement is we need to have a weakly polar solvent, or if we have to use a polar solvent, then there must be aprotic, and the most successful is with non-polar solvent or weakly polar aprotic solvent. So solvent should be, if there is a weakly polar or aprotic solvent should be used. Now, in this nucleus, as I told you, why the frontal side attack is not observed? Why this is the rear side? So, question is, why rear side attack? Now, we have to explain this rear side. What is the cause for this rear side attack? Because in every successful SN2 reaction, the frontal side attack is never observed. So we observe the only rear side attack. Why this is rear side attack? Now look at this. This is nucleophile, which is electron-rich species. This is leaving group. So leaving group is leaving the system with electron pair. If both are on the same side, if the leaving group is moving this side and this attacking nucleophile is coming from this side, both are in the same direction. If both are in the same direction, there will be steric hindrance collision between these two groups. If there is a collision or the steric hindrance between these two, will there be formation? No. So when we say this is the coming nucleophile and this is a leaving group, if they are at a distance of 180 degrees, so the steric hindrance will be minimum. So to minimize the steric hindrance, the attacking nucleophile and the leaving group should be empty to each other. So the first point is to minimize the steric hindrance. To minimize steric hindrance between nucleophile and leaving group. Second reason, nucleophile is negatively polarized electron rich, X minus is again electron rich. If both are closer to each other or if both are on the same side, electron repulsion will take place because both are having same polarity. So if they are on the same side, if the attacking nucleophile and leaving group are on the same side, then there must be enormous amount of electronic repulsion. Because of this repulsion, again the potential energy of the transition state will rise. As the potential energy of transition state rises, the stability will decrease. As the stability decreases, there is no tendency for this transition state formation. So the second point why we should have rear side attack is to minimize the electronic repulsion between nucleophile and the leaving group. Between nucleophile and X minus. Third reason why we should have rear side attack. Now look at this, in the transition state there is simultaneous bond breaking and bond formation takes place. Now for this nucleophile and this leaving group to be bonded to the same carbon atom, these must be on the same p orbital, two different slopes of the p orbital. If both are on the same side, if the leaving group and the nucleophile are on the same side, both will be attached to the same lobe of the p orbital. Now both groups attaching to the same lobe, the extent of overlapping will be very small. If the leaving group and the nucleophile are on opposite side, one lobe of p to the one lobe of p orbital will have a nucleophile, on the other lobe of the same p orbital will have. So to have the maximum overlap, these leaving group and nucleophile should be on the opposite side, that is at a distance of 180 degree. So the third one is to have maximum overlap between nucleophile and the p orbital of carbon atom. That is, let's see, what is happening is we have this carbon, we are focused on transition state, we have this. So as CH bond starts to break, a p orbital is developed on this. So this is p orbital. So as p orbital is developed, hybridization changes to sp2. Now to this p orbital, this nucleophile will bond into the lobes of this p orbital, and on the other side will have the leaving group. So this leaving group, that is X minus. So if both are on opposite side, there is no steric hindrance, there is no electron repulsion, and both will have maximum overlap. Nucleophile will have maximum overlap, that is the rear side. If both are on the same side, then we'll have this. This is the developing p orbital, and both nucleophile and the leaving group will be attached to the same. So this is leaving group and this is nucleophile. So this is Nu minus, this is X minus. So If both are on the same side, extent of overlapping will be less. Second, repulsion will be maximum, steric hindrance will be maximum. So this frontal side attack is not allowed and only this rear side attack is allowed in case of SN2 mechanism. So this is the reason why we need to have a rear side attack in case of SN2. So I have explained all the features that we have observed in case of SN2 reaction. So this is SN2 reaction mechanism. Now we have some important terms, that is a nucleophile. So let me take up some more thing about this nucleophiles. So I shall rub this diagram, because before this let me give you something about this nucleophile. This nucleophile, because how to predict the strength of nucleophile, there are some rules or some examples. Look at this. And this nucleophile may be a positive charge, neutral, or this may be a negative charge. If the nucleophilic atom is same, then the negatively charged nucleophile will always be stronger nucleophile and this conjugate base. So look at this. OH minus is always stronger than H2O. In both the case we have same nucleophilic atom, that is oxygen. So a negatively charged nucleophile is always stronger than its corresponding conjugate acid. Similarly, look at this. ASH minus is always stronger than H2S. We can have a look at this. NH2 minus is always stronger than NH3, or we can say, look at this. OR minus alkoxide ion is always stronger than ROH. So this is the first point. Second point. Now, if the nucleophilic atoms belongs to the same period of a periodic table, nucleophilic atom belongs to the same period of periodic table, then moving from left to right, the nucleophilic character decreases. So look at this. We have the CH3 minus, then we have NH2 minus, then we have OH minus, then we have F minus. The nucleophilic side is carbon, nitrogen, oxygen, fluorine. So all these elements belongs to the same period. So moving from left to right, the nucleophilic character decreases. Third point, if the nucleophilic atoms or nucleophilic sites are same, then the nucleophilic character depends on electron density. Look at this. We have OH minus, then we have OR minus alkoxide ion. We can have look at this. ArO minus phenoxide ion. We can also look at this RCOO minus. So look at this. This is the nucleophilic oxygen. So it is oxygen. Now in case of RCOO minus, look at this. There is a possibility of delocalization. As the delocalization increases, electron density will decrease. So again there is a possibility of delocalization. There is no possibility of delocalization here. So the order of nucleophilic character is RCOO minus is less nucleophilic than ARO minus, which is less than OH minus than OR minus. So look at this. In both phenoxide and carboxylate ion there is a resonance, but the extent of resonance is more in case of carboxylate ion. So carboxylate ion is less nucleophilic than phenoxide ion. So all this depends on electron density. As the electron density increases, nucleophilic character also increases. If the nucleophilic atoms are same, but there is a difference in density. Now, if the nucleophiles belongs to the same group, then moving from top to bottom, nucleophilic character increases. From top to bottom, nucleophilic character increases. That means, look at this, we have this F minus, we have Cl minus, Br minus, I minus. These are haloalkanes. So from fluorine to iodine, fluoride to iodide, nucleophilic character increases. Similarly, look at this, OH, SH, SEH. Again, oxygen, sulfur, selenium belongs to same group. So moving from O to S, S to Sc, again nucleophilic character increases. Similarly, look at this, NH2 minus, PH2 minus, NH2, PH2, ASH2. Again, nitrogen, phosphorus, arsenic belongs to the same group. So moving from nitrogen to PH2, PH2 to AS, again nucleophilic character increases. That is, top to bottom, nucleophilic character increases. Left to right, nucleophilic character decreases. Number 5. Now we have same nucleophilic atom, but steric, yet the bulkiness different. As the bulkiness increases, as the size of attacking nucleophile increases, tendency for these to approach electrophilic carbon will decreases. So as the size of nucleophile increases, nucleophilic character decreases. So look at this, RO minus, R2, CO minus, or look at this, I'll give you this as this, CH3, O minus, CH3, CH2, O minus, CH3, CH, CH3, O minus, CH3. Now look at this, nucleophilic side is oxygen, but the size of group increases. As the size of group increases, tendency for these to approach electrophilic carbon will decrease. As the tendency decreases, nucleophilic character will decrease. So this is a stronger nucleophile compared to this, but whereas in case of basic character, the basic character will increase. So this is something about how to compare the nucleophilic character of different types of nucleophile. Now we'll come to some specific reactions of this SN2 reaction. So we have looked at this Rx, this is alkyl halide. So look at it, these alkyl halides should be primary and secondary. Tertiary does not undergo reaction by SN2 reaction, so we should have primary as well as secondary. Now this reacts with OH minus, this is a nucleophile, so this gives you ROH. That means this is how we prepare alcohol from alkyl halide. This is alcohol. If we start with this OR prime minus alkoxide ion, then this gives you ROR. This reaction is known as Williamson ether synthesis. We are getting ether from alkyl halide. If we react with this RCOO minus, let this be R prime carboxylate anion. This is a nucleophilic site, so we get this R O C double bond O R prime. So we are getting ester from alkyl halide. Take this, we react with this SH minus thioxide ion, we get this RSH thiol. React with this S2 S minus R prime, we get thioether. React with this, look at this NH3, we get RNH3. So this was alkyl halide reaction with this gives you primary amine. Now this RX reacts with primary amine. This is primary. Now reaction with primary, this will give you secondary amine. This is secondary amine. If this alkyl halide reacts with secondary, let this be secondary means 2 alkyl group, then this gives you RN R prime, this is tertiary. If this reacts with tertiary amine, then this gives you quaternary ammonium ion. R prime, and R. Nitrogen positive, this is quaternary ammonium ion. Similarly, look at this, we can have RX reacts with Cn minus cyanide ion, we can get RCN plus RNC isocyanide, depending on whether we use will take a electron. Similarly, this reacts with X prime minus, this is another halogen, when this is Rx prime. We have taken this example, look at this RCl or Br reacts with I minus to give you Ri. Halogen exchange reaction, which was known as Finkelstein reaction during the method of preparation of alkyl iodide. These reacts with RMgX, alkyl magnesium halide. Look at this. This R was negatively polarized. We have this R prime. These also reacts with R2Cul line, dialkyl lithium cuprate Gilman reagent. Again, this gives you R prime. If these reacts with lithium aluminum hydride, that is reduction of alkyl halides with reducing agent, when this gives you RH. So the attacking nucleophile is H minus is acting as a nucleophile. Similarly, we have again sodium borohydride. This again reacts with RH to give you alkane or triphenyl tenhydride. This was method of preparation of alkane from alkyl halide. These reacts, look at this R prime C triple bond C minus, when this gives you RC triple bond C R prime. So this is some of the reactions in which we can have a stronger nucleophile replacing a weak nucleophile. There will be many more reactions. I am just giving you some examples which is often observed. We can also have, look at this SCN minus to R and CS we can have look at this NO2 minus. So we have RONO plus RN2. So this is all the reaction occurring via SN2 pathway. So the requirement is these alkyl halides should be either primary or secondary, cannot be tertiary. That means when we increase the steric crowding around this carbon bearing halogen, the rate of SN2 reaction decreases. So we have to remove the steric crowding or the steric factor to increase the rate of SN2 reaction. So I shall write this. Now, some important point that we have to keep in mind is SN2 reaction never occurs in bridgehead carbon. So if we have halogen attached to bridgehead carbon, now look at this, we have this type of, suppose we have this X. So look at this, this is X, this X is attached to this bridgehead. This is carbon is bridgehead carbon. As I told you earlier, bridgehead carbon cannot assume planarity. So if you look at this, react with this a very strong nucleophile like under SN2 reaction, no reaction takes place. So the reason is SN2 reaction never occurs in bridgehead carbon because these bridgehead carbon cannot assume planarity. Or look at this, since we have this bridgehead carbon, SN2 reaction again requires attack by nucleophile from the rear side. Already we have a bridge, so the rear side is prevented. Look at this, this is the front side. On the rear side we have bridge. So due to the presence of bridge, the rear side attack, nucleophile cannot approach the rear side because of the presence of bridge. So if the nucleophile cannot approach, then there is no question of reactivity. And the rear side attack by nucleophile is prevented by this bridge. So as the rear side attack is prevented, no SN2 reaction takes place in bridgehead carbon. So suppose look at this, we have this. Suppose we have a carbon. This carbon is attached to 4 different groups. Suppose look at this, we have hydrogen, we have deuterium, we have CH3. So we have a chiral here. This is, let's suppose this is I. Now we reacted this with OH minus. So we are using OH minus. So look at this. If you look at this, the priority order is 1, 2, 3, 4. So this is the least priority order group. So in terms of priority, this is 1, 2, 3, 4. So this is least priority order group. So we have to view the molecule from this side. If you view the molecule from this side, this is 1, 2, 3. So this is forming anti-clockwise. If this is forming anti-clockwise, so this is S configuration. Now These OH minus should enter from rear side. If this is the case, then we have this compound hydrogen deuterium CH3. So if you look at this, the priority order of groups, oxygen is 1, carbon 2, deuterium 3, hydrogen 4. Now we have to look at this. This is the least priority order group, so we have to view the molecule from this side. So the order of rotation 1, 2, 3. This is forming clockwise rotation, so we are getting. So A's configuration is converted into R configuration. This is inversion of configuration. Take this. So we have methyl hydrogen. Suppose we have chlorine, hydrogen. Now this is to be reacted with I minus. So I minus being a stronger nucleophile will replace this Cl. So this is under SN2. Now the question says for this SN2 there must be rear side attack. If the rear side attack is taking place, then there must be inversion of configuration. So the configuration will be look at this. Now Cl3 and Cl was on the same side. Now this is an opposite side. So this is what we call as inversion of configuration. Now look at it. If suppose we have this is CH3, this is Br hydrogen, and this is C2H5. Suppose we have this. Now this is to be reacted with OH minus. Yeah, take this case. Okay, this is OH minus. Now this reacts with this. When we say okay, this is undergoing SN2 reaction, so there must be inversion of configuration. Then the product will be CH3 OH 8 C2H5. Now let's see the configuration. Order 1, 2, 3. This is forming clockwise, but the least priority order is on horizontal side, so this must be opposite. Clockwise means this is anti-clockwise. Observe is clockwise, so actual should be anti-clockwise. Look at this. 1, 2, 3. So this is forming anti-clockwise, but the least priority order group is on horizontal portion, so this must be axially reverse. So we get this R. So A's is converted into R, that is Walton inversion product. Take this, we have this N-butyl bromide CH3, CH2, CH2, CH2 bromide. Now this is to be reacted with KCN, potassium cyanide. Now this is primary. We have a Cn minus, which is a strong nucleophile. So this reaction must take place by SN2, when this gives you CH3, CH2, 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 Cn. Now let's see the mechanism of this reaction, how this reaction proceeds. We have to write out the mechanism. Now this can be written as, we have this carbon. This carbon, look at this is a carbon bearing halogen. We have 2 hydrogen here. This is suppose look at this C3H7. So we have hydrogen here. Carbon is having 2 hydrogen. This is C3H7. We have this Br. Now this reacts with Cn minus. So according to this Cn minus will approach from rear side and this goes from the front side, and this gives you a transition state in which both the leaving group and the attacking nucleophile are attached to the same carbon and the remaining groups are remaining as it is. This is hydrogen, this is hydrogen, this is C3H7. So we have a transition state, and negative charge is transferring from carbon to the living group, and finally this gives you the product, that is NC, with the bonding is through carbon. So we have C3H7. This is how this reaction takes place. Substitution reaction. Look at this. We have this CH3I methyl iodide. This reacts with OH minus hydroxide ion, when this gives you CH3OH. Similarly, look at this. We have this CH3CH2 I react with CH3O minus methoxide ion. Now when this gives you CH3 CH2O CH3, that is I minus is replaced by CH3O minus, so we get this ether. So this is how this SN2 reaction takes place. Now I'll just give you the energy diagram for this SN2 reaction. We have told you this occurs in a single step reaction leading to the formation of transition state. Any factor which increases the stability of transition state will increase the rate of reaction. Any factor which decreases the stability of transition state will decrease the rate of SN2 reaction. Energy diagram for this SN2 reaction. This is a reaction coordinate. This is potential energy. We have this is the reactant Rx plus nucleophile. This is the transition state. You can look at this, NuRx. This is transition state. This is the product RNU plus X minus. So this is potential energy. This distance, let's define this distance as this is the enthalpy of the reactant. Let this be the reactant. This is the enthalpy of product. This is delta H of transition state, and this is this energy gap. This is the activation energy of forward reaction, and this energy gap, this is what we call as enthalpy of reaction. Now look at this. If by any factor this energy gap can be decreased, then the rate of reaction will increase. If delta HTH is decreased, the rate of reaction will increases. So rate of SN2 reaction increase means you have to decrease this delta TH. Now this delta TH कैसे डिक्रीज करेंगे? That means we have to decrease this activation energy. If activation energy is decreased, then the rate of SN2 reaction will increase. So activation energy कैसे decrease करेंगे? There are two options है. We increase enthalpy of the reaction. If enthalpy of reaction is increased without changing this delta TH, then this energy gap will be decreased. As energy gap is decreased, the rate of reaction will increase. Or if enthalpy of reaction remains as it is and V decreases enthalpy of transition state. So by decreasing enthalpy of transition state without changing enthalpy of reaction, if transition state can be stabilized, then enthalpy of transition state will decrease, so energy gap will decrease, so rate of SN2 reaction will increase. But if activation energy is increased, rate decreases. So this increase in activation energy is again possible in two different ways. If enthalpy of reaction is decreased, means if reactant is more stabilized, the potential energy of reactant will decrease, then this energy gap will increase, rate becomes slow. Or if enthalpy of transition state is increased, means if transition state is destabilized, then activation energy increases, rate of reaction decreases. So by any means we have to decrease this energy gap. So to decrease this energy gap, we need to have a polar aprotic or weakly polar solvent. We need to have alkyl iodide. We need to have primary alkyl halides, that is less sterically hindered alkyl halide. So this is energy profile. And one more thing that we have to keep in mind is this SN2 reaction always competes with E2 reaction. Competes with E2 reaction. But by changing the reaction condition, we can increase the quantity of substitution or we can increase the quantity of elimination. So for this, look at this point is substitution favors at low temperature. So if temperature is decreased, then the quantity of substitution increases, quantity of elimination decreases. But elimination E2 favors at high temperature. So if with the same reactant reagent, if reaction is carried out at high temperature, then elimination is favored, substitution is less favored. That means eliminated product will be forming as a major product, substitution will be forming as a minor product. Second, look at this. Substitution bimolecular is favored at strong nucleophile, whereas elimination is favored in presence of strong base. So if nucleophilic character is increased, then substitution product will be dominant. If the basic character is increased, then substitution will favor. Then the third point is we have to keep in mind the alkyl halide. So for this SN2, order is primary, most reactive, secondary, tertiary one does not react. But if we have E2, for E2 the reactivity order is just the reverse. Tertiary is the most reactive, primary is the least reactive. For both involves transition state, both involve single state. In both the case we require a weakly polar or non-polar solvent. Both order is 2, both molecularity is 2, both occurs in single state, but there is always a competition here. So for this we have to check temperature as well as the basicity or the nucleophilicity. I'll just give one example here. Take this reaction CH3 CH2 Br bromoethane. Now this reacts with aqueous KOH. So aqueous KOH dissolved in aqueous. So these act as a strong nucleophile. So in presence of aqueous KOH, substitution reaction takes place. Since this being a primary reaction presents a strong nucleophile, so reaction has to be SN2. So we get this CH3 CH2 OH and KTR is formed. But if the same alkyl halide is made to deal with alcoholic KOH, so alcoholic KOH, this becomes a strong base. So we have alkyl halide plus strong base, so the reaction will favor E2. So this gives you CH2 double bond CH2. So the reactant reagent is same, but in one case we are increasing the nucleophilic character, so SN2 is favored. In the second case we are increasing the basic character, so elimination is favored. So this is by changing the reaction condition we can change the outcome of the reactant. Look at this again. CH3 CH2 take this I CH3, we use aqueous KOH, that is at room temperature. Now we use same aqueous KOH but at high temperature. So in both the cases we are using aqueous KOH. Room temperature, so reaction will favor substitution. High temperature, reaction will favor E2. So this gives you CH3 CH double bond CH2. So this will favor CH3 CH OH CH3. Substitution is favored. So this is the interplay or the competition between SN2 and E2. So hopefully you enjoy this SN2 reaction. This is a rough idea, a rough picture, a broad picture of SN2 reaction. Is it clear? Okay, bye.